All right. So in the previous class, we had discussed the Newton-Raphson method, right? You remember that? So there were 3-4 steps that we had very clearly identified as a part of Newton-Raphson method. The 0th step, you can say, was to identify a point of equilibrium, okay, which exists and which you are aware of. Fine. So usually 0, 0 is the point of equilibrium when there was no load and there was no displacement. For typical load type of analysis, where the loading is applied, non-loading is applied, and you have to calculate the deformations. So 0, 0 is the initial point. Then the first step was to calculate the tangent stiffness of the system, correct? The second step after the tangent stiffness was to calculate the deformations, right, for the tangent stiffness. So that deformation was basically unbalanced force divided by the tangent stiffness would be the deformations in the system or displacements of the system. From those displacements, we calculate internal deformations of each member. Okay, and that internal deformation calculation and subsequently calculation of internal forces in each member was called, what was the name given to that thing, that step?
State determination.
Correct. So state determination is basically from the displacements that you calculate. So displacements is nothing but you have this unbalanced force P1. If we have this unbalanced force P1 and we calculate the tangent stiffness K naught or KT naught, okay, so P1 divided by KT naught gives us UA, that is displacements, right? Displacements at the nodes. From those displacements which are available at the nodes, we calculate the deformations of the members. Okay? So member deformation calculation, and then internal force deformations, internal force calculations. These two things combined are called state determination. So state determination will tell us that actually we were hoping that the force will be P1, but when we actually look into the member behavior, we find that the forces are only this much, which is marked by this location, this height. Okay, so then that is the still unbalanced force, the difference between P1 and whatever force we got as an internal force. So then once we calculated the internal force, there was one minor step that I missed just now. So from the internal forces, you have to again assemble all the internal forces, add all of them up, and see how much of imbalance is there from the external forces that were applied. Okay, and that is that imbalance. Then the next iteration starts. You got the unbalanced force, correct? You calculate the new stiffness matrix, or new stiffness, tangential stiffness that is, and then calculate the new displacements. And then for those new displacements, you calculate the internal deformations, internal forces. That is again second iteration, state determination. Once you know the internal forces, you add all of them, and you will see that some of them will cancel out, but some of them will not cancel out, and that is again the imbalance. Okay? And that's how you keep going until the errors are very small to the acceptable level. So we had solved these two problems. First problem was pretty easy. Two springs in series, a known load is applied. We could solve it directly in a jiffy way, in a single step, because both springs are in series. So 5 kilonewton you can apply to both springs. We were able to solve it very quickly, directly. But then we used the Newton-Raphson method to solve it. So of course, it didn't make much sense to use the Newton-Raphson method because you could solve it directly. But when you go to a slightly more complex issue problems, wherein there are 3 springs and there are 2 in series and 1 in parallel with the remaining 2, then you will see that solving for any given load becomes relatively difficult because one of those springs is a nonlinear spring. Okay, so the direct formula cannot be applied as easily, and as a result, Newton-Raphson method does offer a slight advantage. So we developed the stiffness matrices, we followed all the steps that we had discussed, and we did 3 iterations. By the end of 3rd iteration, I believe, we had very small unbalanced forces, 0.003, in comparison to 10 kilonewton that was applied. This lack of balance or this unbalanced force is very small. So then we could say that this is almost converged. Fine? Is that fine? So I hope I have done a little bit of recaps to refresh your memory. Right? So this method is known as Newton-Raphson method. Of course, the examples that I've given or I've been able to incorporate in the classroom lectures are on very simple problems. Often when we deal with real structures, this is how we do it typically. So I'm not giving you a solved example. I'm just discussing some ideas here. Okay. So let's say I have a frame. Okay. You can see my screen, right? I'm scribbling something.
Yes, sir.
Yeah. So
Yes, sir.
we apply a lateral load on this frame, and there will be some kind of a deformed shape. Somewhat like this. Okay. These angles remain 90 degrees. Fine. So if you draw the bending moment diagram, I'm sure you must have drawn such bending moment diagrams 100 times. You would see that you would get very large moment demands at these hinges. Okay. And let's say you are designing or you are analyzing this system for the cases where the load is large enough, this P force is large enough so that the member here starts to yield. Okay. So there can be 2-3 ways of doing it. The way SAP 2000 typically does is SAP 2000 has the capability to do pushover analysis. Okay. So in a typical pushover analysis, you have all heard of SAP 2000, right? Or STAD, or not STAD, sorry, ETABS.
Yes, sir.
How many of you have heard of ETABS or SAP 2000?
Yes, sir.
Yes, sir.
Yes, sir.
Almost everybody. Yeah. So ETABS is a more commercially used software for real structures, and SAP 2000 is more scientific. Okay. So if you want to test an idea or concept, you would rather use SAP 2000. It is more bare bone. It does not have too many features available for designing various kinds of structural elements, but it is more robust also. Okay. So I have more experience with SAP 2000, but if you have been a design engineer, then you would be more familiar with ETABS. They are from the same company. So when you do a pushover analysis, basically what you do is you keep pushing it until the structure collapses in a way, right? And collapse is kind of a tricky term. So what it does is it assumes some kind of a lumped plasticity, lumped hinges. What does that mean? What it means is that for typical structures which are like these, usually what happens is that bending moment diagram is not uniform. Bending moment diagram varies like this. Okay, let's say I'm drawing it on the column. So it typically varies like this. So there is nonlinear non-uniform bending moment in the cross section. It is highest at some location, lowest at some location, and again negative highest at some other location. So what happens is that since the maximum bending moment is confined to a particular band or particular area, what you can assume is that this member, actually this column, instead of being made as a completely uniform cross section, you can think of it as the rest of the column behaves elastically, but there is a hinge, which is a plastic or nonlinear hinge sitting here at the base, which is likely to plasticize. Okay, so the rest of the structure, this part of the column, if you take a segment here, a small segment, let's say a segment of length S. Okay, for that segment, when it bends, this is that segment S. When it bends, it forms an angle, right? This angle is theta. This is that segment S. So if I plot this theta versus moment, so if I increase the amount of moment, the theta increases. You agree? So for this part, you assume it to be linear forever. Okay. So this is everywhere else, but I'll not write it in a minute. But for this part, let's say there is some literature, specialized literature available, which says that the hinge formation is usually distributed over a length, and that length values are given based on the cross section and various properties. Let's say some value d. Okay, just I'm assuming a value length d. So over a length d, that hinge is forming. Okay, and for that d, now imagine that this is that d length of the column. It's so hard to draw. This is the fixed boundary condition. The column is extending here. This is the cross section of the column. Okay. And then over a length d, this is where it is plasticizing in a way. Yeah. So this length was originally d, and then the rest of the cross section remains elastic. So for this portion, initially it will have the same stiffness, but at some point it will plasticize. Okay, and then it may start going down also. So such kind of curves are available for hinges. So for example, if you have an RC section which has certain amount of reinforcement and some shear reinforcement, you go to there is basically SAP 2000 or ETAPS. They already have incorporated this literature. So there is a lot of research done on these where people have developed these curves. Okay, these are called hysteresis loops. So hysteresis loops is particularly useful when you are dealing with a cyclic loading, which is true for earthquake, but even otherwise also such kind of backbone curves are available. So which basically says that when you load it, if it is hinges forming, then it will follow this path and it will go this way. If the hinge is not forming, it will follow this path. So what they say is that the hinge is confined here. So basically they change this system. This is basically a distributed plasticity or distributed hinge system into a lumped hinge system, as I've explained here. So one hinge exists here, other hinge exists here. Maybe you can put more hinges. Maybe the beam is slightly weaker, so another hinge exists here, another hinge exists here, and the rest of the system remains linear. So this part is linear, this part and this part is also linear. And all the nonlinearity is confined to these hinges, these four hinges. Okay. And this is a very acceptable, very powerful model. So basically what happens in this case is you get one element, two element, third element, fourth element, fifth element, sixth element, seventh element. So a problem which was actually three elements, three frame members were there, right? In this problem originally. Now you have divided that into 7-member problem. Okay. You get me? So you have your stiffness matrix now will have 7 members to assemble, and then all the degrees of freedom corresponding to those members. Got it? Alternatively, you can also have some softwares like, for example, ANSYS or Abacus. I use Abacus more often. What they allow you to do is, this is your frame, same frame I'm studying, let's say, made of beam elements or frame elements. Okay. Instead of saying that the entire member is, this entire column is a single member, they recommend you to divide this into smaller segments. Okay, that is called meshing. Yeah. So at each joint here, you have a node, and then this is one element. Likewise. So you divide this into smaller segments. You mesh it. Then, depending on which type of element you are using, the software allows you to incorporate distributed plasticity. So this is not lumped plasticity, it is distributed plasticity. What it means is that if, let's say, I apply a lateral load like this, the bending moment will be, initially the entire system will be linear. It will be behaving just like a linear system. But as the bending moments start to increase in some of these elements, they will going into plastic zone. And then automatically the software will keep calculating. So let's say this is the cross section with some reinforcement. Okay. And the software will basically, in a way, keep calculating as the curvature is increasing, how the moment will change. Okay. And then in this particular case, the hinge can form anywhere. You don't have to know beforehand where the hinge will form. Each element has the potential to behave like a hinge. Okay. You are following me, right? So for example, in this particular case, let me go back here. In this particular problem, this kind of a problem, or in this problem, if I had a concentrated load acting in the middle, then this kind of a hinge definition will not work. So I should have defined a hinge here if there was a concentrated load acting here. Until I define that hinge there, the software would not know, and it will not incorporate the plasticization according to that. But in this problem, I don't have to do that. I can apply any kind of a load. It will automatically take care of it because there is a potential to hinge forming of a hinge anywhere. You're following me? And then there is no empirical relationship required. So in the previous case, you needed some empirical relationships in the lumped plasticity. Empirical relationships for the hinge. This is m theta relationship for the hinge. So as the cross section changes, this empirical relationship changes, but most of these relationships are developed for various types of parameters. So the software can automatically calculate that. But in case of a distributed plasticity, this kind of a modeling, these empirical relationships are not required. This kind of empirical relationship is not required. You can simply analytically derive the M versus phi curve for any cross section, and that software can do it inherently. That is basically it aggregates or it integrates the cross section fibers. So it can divide the cross section into 7 or 10 or whatever number of integration points and calculate the net properties. Fine? You guys are following me?
Yes, sir.
Yeah.
Yes,
All right. So whatever we have discussed in the examples, so like we have given the examples of 3 springs, wherein their total degrees of freedom was 1, 2, and 3 only, right? The total 3 degrees of freedom were there. As soon as we increase the degrees of freedom, the problem becomes pretty difficult to explain in the classroom, and you have to use a program. So I'm just giving you an idea here how to incorporate that. It is not that hard. In fact, the program that you have, once you write the program for a plane frame, you just have to make a few changes to make it work for even a Newton-Raphson scheme. You have to basically put the Newton-Raphson scheme framework around it. So the program will go into the Newton-Raphson scheme, and you keep calling this program, the main subroutines of the program, into the Newton-Raphson scheme. So the same program can be incorporated into Newton-Raphson scheme to solve it for a nonlinear problem. Okay. Anyway, I'll not be able to spend any more time on that. Somehow the way this course is designed, we don't have enough time to discuss solving of nonlinear problems in much detail. I hope I'm able to generate some interest in you so that you can pursue it on your own. You can read some textbooks on solving nonlinear problems. In addition to Newton-Raphson scheme, there is also one very powerful scheme which is called arc length method. So as I had mentioned, if you remember, Newton-Raphson scheme works okay as long as the stiffness does not become negative, okay, or just before it becomes 0. Till that point, the Newton-Raphson, so this is displacement, this is force, and I'm saying in generic terms. So as soon as the overall stiffness becomes singular, your Newton-Raphson method does not work. So this is pretty much the limit of how far you can solve it. You can solve it here very easily. You can use Newton-Raphson to solve into nonlinear domain also, but not beyond this point. But you can use arc length method to solve it beyond this point also. So if there is an unloading part due to damage or due to reduction in stiffness, even that part can be taken care of using the arc length method. You can keep solving it all the way. So please, if you are interested, you are welcome to read about arc length method and try and see how you can incorporate that in your research. Okay, we will see how to use nonlinear Newton-Raphson method to solve a problem which is geometrically nonlinear. Yeah. So the earlier 2 problems where the spring properties were changing with deformation, which was more akin to a material nonlinearity problem. Correct? It was almost like there were 3 members. One member was plasticizing, isn't it? But this problem, the one that we are going to discuss now, is geometrically nonlinear. Can you see why is it geometrically nonlinear?
Imperfection.
Yeah, Virender? Yeah, sorry. Repeat again.
Initial quickness, sir.
Initial imperfection, yes. So yeah, correct. So this is a column. If you read the description here, basically what it is saying is that this is a rigid column. So the member itself, the bar or the column, that itself is rigid. So it does not deform at all. Okay, but it can move. You understand the deformation, the difference between movement and deformations, right? Movement can be a rigid body movement. I have this pen, the pen is moving, but it is not deforming. For it to be deformed, I have to apply this kind of a force and make it bend or make it stretch. That's deformation. So this is a rigid bar which can move but does not deform, which is held through a spring at the base. This is spring, which is a rotational spring. Vertically, at this point, it cannot move vertically because it is supported on this pin support, but it was able to rotate freely. But in addition to that, a rotational spring is provided here. Now it cannot rotate freely. The way rotation spring is, somehow it was supposed to keep the bar vertical, perfectly vertical, but the spring was not calibrated correctly, and somehow the spring in its neutral position, when the spring is not under any kind of stress, is completely free. Okay, it is not stressed. The spring is completely free. At that time, the column is not, or the bar is not perfectly vertical, but at a slight angle from vertical, and that angle is very tiny. Okay, so that is an imperfection. It was supposed to be perfectly vertical, but that angle is 1 divided by 1000. That's a very small angle, but nevertheless, it is there. Okay, and then the bar was supposed to resist some vertical loads. Okay, so I apply a vertical load on the bar. The load is perfectly vertical. Okay. Now the issue is that if the bar was perfectly vertical to start with, and the load was also vertical, there was no challenge, there was no problem, there is no geometric nonlinearity involved. Correct? Because the bar would have simply taken that load axially and transferred it to the support here. Correct? However, now since the bar is not vertical to start with, this load is applied. This load is going to introduce some moments here, some moment demand here, right? And that moment has to be resisted by the spring. So we want to see for a given load, how much will be the deformation of this spring, or how much will be the rotation of the bar. The bar can rotate, move, that is freely rotate. Fine. So we will try to use Newton-Raphson. Of course, you can derive this very quickly using analytical scheme, any kind of analytical scheme. You can use energy-based principles, or you can use simply equilibrium to solve for it, and you can get the deformations. But we will use Newton-Raphson method for this one. So it is given to us, since Newton-Raphson method is a numerical method, we have to start with some number. So instead of saying that this theta is some random value or theta, I cannot work with theta, so I have to know some number. So I'll start with 1 divided by 1000. So theta 0 was 1 divided by 1000. That is the angle. So how much is the deformation, or how much is the displacement here from vertical? This was perfectly vertical position, and actually the bar is here when no load is applied. So what is that movement or displacement?
L by 1000.
L, correct. L divided by 1000. Agreed? So the column is off the plumb. You know the plumb, right? Plumb is perfectly vertical line. So off the plumb by L divided by 1000, or 1 divided by 1000. Fine. So, and at that stage, when the column is sitting here in this position, what is the stress in the spring? I have not applied any load here at this time. Yes. So the spring is correct. So a spring is completely stress-free. It is not under any kind of stress. It is not stressed. It is perfectly free, and I have not applied any load here at that time. The column is just freestanding, supported by this spring. Okay, and column has no weight of its own. Fine. Now that means there is no moment acting here either. So the column has no weight. There is no load. So column will remain in this position, and spring is completely free. Next step. Now let's say I apply a load P here. Fine. So axial load is P. That will be resisted by another load P here. So if I may just draw on top of this itself. There is load P acting here, and there is load P acting here. What will be the direction of this load P? Perfectly vertical, because the two forces have to balance each other. Right? However, when the two forces are balancing, the moments that are arising out of them are not balanced. If I take the moment, external moment, how much will that be? This is P force, which is at an offset from this P force. And how much is that offset? L divided by 1000, right? So the external moment will be PL divided by 1000. Agreed? That external moment, that is the external demand. But at that time, if the column is still in this position, it has not moved from this position. What was the spring force or spring moment? When the column is still in this position at at 1 by theta rotation, spring was at 0 moment. So M internal was 0. Correct? So then this is the unbalanced force which is not resisted internally. So it remains unbalanced. So unbalanced force will be M external minus M internal, that is PL by 1000. That is your unbalanced force. Fine. Now, so we have calculated in the Newton-Raphson scheme. First we calculate the unbalanced force or unbalanced moment. In this case it is moment. Then the second step was calculation of stiffness matrix or stiffness. Okay. In this particular case, you will see that the stiffness is not changing. Even though the configuration is changing of the system, but the stiffness remains constant. It is given as K. The stiffness of the spring is K, which does not change. Still, the problem can be nonlinear, even though the stiffness does not change. So stiffness is K. Third step, or the 2.5 step, you can say, is calculation of displacements, new displacements. Right? How much will that be? This was the unbalanced force. This is the spring stiffness. So unbalanced force was PL by 1000 divided by K. So this is the additional displacement. So basically what it means is that this is the vertical line. This was the originally the bar configuration. But because of this P that I have applied now, the bar will rotate further to this position. Okay. And how much is this rotation? This delta theta is PL by 1000 K. Agreed? Now, because of this additional rotation, what has happened is that my external force demand has also increased. Because earlier this P force was acting at a distance of L by 1000. Now it is not acting at L by 1000, it is acting at L by 1000 plus this multiplied by L, right? At a slightly farther distance. So P has also moved, right? So there will always be some unbalanced force. Agreed? So this is the first iteration. In the first iteration, we got the deformations. The deformation turns out to be, the additional deformation turns out to be PL by 1000 K. Correspondingly, that is the displacement plus that is the internal this is the total displacement 1 by 1000. That is the original one, theta 0, plus in the first iteration we got PL by 1000 K. The external moment, because external moment is basically directly dependent on what is the total deformation. So external moment depends on where the P is with respect to the perfectly vertical line. Right? So that is theta 1 multiplied by P. So just multiplied by PL. So PL by 1000 plus P square L square by 1000 K. Agreed? This is your external moment. The internal moment, however, that is the resistance from the spring. For that, you have to deduct the theta 0 part, because when theta 0 was the displacement, there was no internal resistance. So out of theta 1, you remove theta 0, that is this part. So only PL by 1000 K. So PL by 1000 K multiplied by K. That will be the internal moment. That is PL by 1000. And then there will be subsequently an unbalanced force, which is unbalanced force is M external minus M internal, which is P square L square by 1000 K. In the previous step, it was PL by 1000 K. Sorry, unbalanced force was PL by 1000. Now it is P square L square by 1000 K. Okay. We do one more iteration like that. This time the unbalanced force is P cube L cube by 1000 K cube. So you can see that PL by K term is multiplying, right? Likewise, if you look at the deformations, in the first deformation was 1 by 1000, second or zeroth deformation was 1 by 1000, second one, the first one I got 1 by 1000 plus PL by 1000 K. The second iteration I got 1 by 1000 plus PL by 1000 K plus P square L square by 1000 K square. Compare this with this. So PL by K terms are continue to be multiplied with subsequent terms. And as you keep going in iterations further and further, you will see that theta final will be 1 by 1000, that was initial imperfection, plus PL by K times that, plus PL by K times that, plus PL by K times that, and so on. Right? So this is a geometric series we got. If you want to calculate theta final, we can say we can take 1 by 1000 out. It will be 1 plus alpha square and so on. This is a geometric series. For what value of alpha can we have a solution for this? If alpha is more than 1,
Alpha should be less than.
yeah, so alpha should be less than 1. As long as alpha is less than 1, you can have a solution for that. That means alpha being less than 1 means PL by K should be less than 1, or P should be less than K by L. So that is the limit of stability. So as long as your P is less than K by L, you will have a theta value, which will be the final theta. That means there won't be any further deformation. But if P exceeds that KL by L value, then you will have an unstable system. That means your theta will be infinity. As long as your alpha becomes greater than 1, this part will be infinity. So theta will be infinity. Got it? Looks okay, right?
Yes, sir.
Yes, sir.
Yeah. So basically, this is one very simple problem which is kind of showing you how to incorporate Newton-Raphson method to account for geometric nonlinearity. Typically, the way we incorporate geometric nonlinearity in real life problems, basically what we were doing in this process was we were only, let's say this is the frame, and we have some P load acting here, and then we apply a V load here. Okay, and because of these two combined effects, the frame deviates or sways like this, and then there will be P delta effect, right? Because P also move along with it. The new position of P will change. So all we have to do is, in our stiffness matrix when we develop, so for this frame, we would develop the stiffness matrix for this member first, and then we will transform it in the global coordinate system. So global coordinate system will be X, Y, and this one is local X, Y. So this is perfectly aligned with X, Y, no issues. This member, it will be local X, local Y, right? This is global X, global Y. So I'll simply align them perfectly fine, no issues. What happens is that as the deformations take place, the member, instead of being here, moves to this location, right? So the two joints, I and J joints, or J and K joints, they move here. Likewise, these joints move here. In between, the member is deformed, of course. Right? So as we had decided beforehand that our local X has to go from J to K. But typically, as the member deforms, we don't change our local X direction. We continue to assume that local X is in this direction, XM is in this direction. If you change that, so every time, let's say you apply some V load here, V is given as, let's say, 1000 kilonewton. You apply, instead of 1000 kilonewton, you apply 5 kilonewton first. You calculate what is the deformation, right? And for that deformation, you revise the value of XM. So now your new XM is this one, not this one. XM is not this one anymore, it is this one. And for that XM, you do the transformation. So when you do the S global, that is stiffness of global stiffness matrix, that is assembly of S member, right? Assembly, before this one, you also do the transformations of each member. those transformations, instead of doing it with respect to xm here, you do with respect to xm here. Okay, and if you do that, it will automatically take care of the geometric nonlinearity issues mostly. Okay. However, that process somehow becomes more cumbersome because there are too many iterations you have to do. For every single iteration, you have to revise the stiffness matrix, which will become slightly cumbersome. So there is an analytical approach of calculating geometric or accounting for geometric nonlinearity of a problem. I'll try to spend maybe today's whatever time is remaining in the next class to talk about geometric stiffness matrix. Okay, so you have learned about stiffness matrix of a plane frame problem, right? So if I can open that slide, you have seen this stiffness matrix. Have you seen this stiffness matrix so far? This is K is equal to EI by L. Let me project it. K is equal to, that is stiffness matrix, is equal to EI by L, A by I, 12 by L square, 6 by L. These terms you have seen?
Yes, yes, sir.
Yes, sir.
Yeah. I'm not always written in that form particularly. If you take EI inside, right, then you would know. So this is basically AE here, the very first term. If you take it inside, so it is AE by L. This one is 12 EI by L cube, and so on. So these terms you have seen. This is the stiffness matrix of a plane frame. Analytically, people have been able to derive the expression for a stiffness matrix of a member which has deformed. Okay, so this is perfectly fine if the deformations are very small. So let me draw a little. So if there was a frame member, you had P acting and you had some moments acting. Okay, and because of these moments, the member deforms this way. And in addition to that, there is P also applied. So because of P, this will be amplified. Fine. So if this P was not very large, or this member deformations were not that large, that this P's effect on this deformation will be secondary moment, and that secondary moment are to be ignored, let's say, then this stiffness matrix was sufficient. Okay. But what happens is that because of these deformations that you can see here, and P is acting, because of that, the deformations will be further increased because of the presence of P. So these deformations, earlier we were assuming that these kind of deformations that you are seeing here, this deformation is only purely because of these M, right? Lateral deformations are only because of M. But if P also starts to interact and produces secondary moments, which will further increase the deformation. This was the original one, but then you get a enhanced or amplified deformations. Then how do we do that? So we have been, what we'll try to do in the next class, in today's class, is derive the secondary part of this stiffness matrix, which is a function of P itself. So as you increase the value of P, you will see if the P is compression, it is negative. If P is tension, it is positive. Okay, so this negative sign is to be used if the P is in compression. So basically what happens is that overall stiffness of the member decreases as the P value increases. You understand? And this is the additional stiffness. And most of these softwares, let's say Instad or SAP 2000, in most of these softwares, when there is a button which says switch on geometric nonlinearity. Okay, and as soon as you switch on that button, it basically stops ignoring this matrix and starts to include this matrix into this calculation. That's all it does. Okay. In the class today and tomorrow, we will see how this matrix came about. We got this matrix, this secondary matrix here. So this is called geometric stiffness matrix. Okay. All right. So let's do some derivations. So I think I've given you enough background into what is amplification, what is the secondary moment effect, right? You are familiar with that. So I'll directly dig into the derivation. And you have to pay attention because it can be a little bit boring. Yeah? So don't lose focus. And this derivation actually I've taken from a textbook wherein the sign convention was slightly different from what we are familiar with, what we are typically used to. So the moments that are in clockwise direction are considered positive here. So I hope it won't be too confusing for you. This is a frame member. To start with, I'm assuming a simply supported boundary condition here. Okay, so that means it cannot move in this direction at these two locations. At this location, at the two ends, it cannot move in the lateral direction, but it can move in the axial direction. And anywhere in between, it can move in the lateral direction. So there is an axial force P acting, and there is a moment MA, positive moments, external moments. MA and MB are acting. What is A and B? A and B are the two ends. Fine. So if that is the case, what would be the end moments? End moments are given. What would be the shear forces at the ends?
MA minus MB by L.
MA minus MB or plus MB? I have drawn them, both of them, in the clockwise direction.
Plus, sir.
Yeah. So at this end, it is pulling it down by MA plus MB divided by L. At this end, it is pushing it up by MA plus MB divided by L. Agreed? So now, if you see, it is in perfect balance. MA plus MB divided by L multiplied by L will balance the moments, and P are balanced. And because of these moments, MA and MB, there was a deformation in the beam or the frame. And let's say the deformed shape looks somewhat like this. Okay, make sense? Now, if I draw the free body diagram of its initial portion, initial Z length of this member, so starting from here, I'm going Z length. Okay, and at Z distance, the deflection is, let's say, V. So this is the deformed shape of the beam. Okay, again, the forces that were acting here, basically what I'm trying to do is, I'm trying to calculate how much is the moment and axial force acting here. So there was a force P acting here. There was a vertical force MA plus MB divided by L acting here. There is a moment MA acting here. Right? What will be the vertical force here? It has to be exactly equal, otherwise it won't be balanced. Right? It is inconsequential, so I'm writing it, but it doesn't matter. There will be a horizontal force P acting here to balance the other horizontal force P here. Okay? And there will be a moment acting, I'll call it MZ. Okay, and what I want to know is how much is this MZ. So we can write equilibrium equation, which will be basically MZ is equal to MA plus P times how much? Secondary moment I'm saying. The two P values are not aligned. So P times V, right? So P times V is giving me a clockwise moment. MA is also clockwise. P times V is clockwise. And the MA by MB divided by L is anti-clockwise, so minus. Multiplied by what?
Z, sir.
Z. Correct. Okay. So I'm just asking these random stupid questions just to keep you on, keep you awake. Otherwise it can be sleepy. And when the mathematics starts, it will be further. So now we know that EI V double prime, V is the deformation, right? V double prime is equal to or plus mg or equal to minus mg or plus mg equals to 0. Agreed? So let me see. So now mz I can substitute here. What do I get? ei v double prime plus ma plus pv minus ma plus mb z divided by L is equal to 0. Is that correct? This is the differential equation where I've got terms of v double prime and v. Okay? And then this is the constant term. This and this are the constant terms. Okay? So let me write that in the form that you are familiar with. V double prime plus, I can write it p divided by ei. I'll call it k square. So k square is nothing but p divided by ei. Okay. So v double prime plus k square v is equal to, this will go to the right hand side, ma plus mb z by L divided by ei minus ma divided by ei. Okay. So this is a differential equation. You all know the solution for this differential equation. V will be equal to a sine kz plus b cos kz, right, plus ma plus mb z L ei k square, right? It will satisfy the equation, right? So as you do k square multiplied by v, this term k square will go away, and second derivative, this term will go away. So we will be left with this term exactly. You are with me, right?
Yes, sir.
Yes, sir.
Does it look okay? So this will be a solution to this equation, right? Now, how do we get the values of these two coefficients? By applying the
Boundary condition.
boundary conditions. So to start with, I have two boundary conditions. V at V at z is equal to 0 is how much? And V at z is equal to L is how much? 0. Okay. So at both ends, the deformations are 0. So I substitute that, and these two conditions, basically, I substitute z is equal to L in this equation. What do I get? I get A is equal to, first I get B is equal to, from this equation, I get B is equal to M A divided by EIK square. And I get A is equal to minus MA cos KL minus MB divided by EI K square sine KL. Okay. This is obvious. This first one, B, was very straightforward. You simply substitute z is equal to 0. So sine, this term will become 0. The second term will become B. The third term will become 0. So B is equal to MA EIK square. This is straightforward. For the first, for A value, you have to substitute the value of z as L. So B was already known to you. So you can get the value of A, which turns out to be this much. Fine. So with the knowledge of A and B, what have we got? Basically, we got the value of V everywhere. Okay, so I'm not writing this thing again, just to avoid save some effort. This is the expression of V, wherein A and B are given by these equations. Okay, and this is in this B. In this beam, at any given location, at any given z, this is the V value, and that V value is given by this expression. This expression here. Okay. Now you remember what our ultimate goal is. Our ultimate goal is to develop the stiffness matrix, and the stiffness matrix relates what to what. This is my beam, or this is my frame member. Okay. What I am interested in, and somehow for the time being, I have assumed that the ends are not moving. So the ends are not moving. So which are the degrees of freedom? Deformation along anywhere along the length of the member. Those are not my degrees of freedom. What are my degrees of freedom? My displacements here could have been degrees of freedom of interest, but for the time being, I'm assuming them to be 0. Then what is the other degree of freedom that I'm interested in? Or what deformation?
Slope.
Rotation.
Rotations, right? So these are the theta values, or you can call it theta, or you can call it in terms of V. What do we call them?
V dash.
Yes. So that is what I'm interested in. Hence, I'm not interested in knowing the V value or V prime value everywhere. Primarily, I'm interested in knowing the theta value or V prime value at the ends. Okay. So V was given to me. I can calculate V prime from there, right? So V prime is the derivative with respect to Z. So A and B don't have any terms corresponding to Z, right? These are constants. A and B are constants. So I don't have to really substitute the value or worry about A and B, but anyway, I'll do it. So the derivatives with respect to sine Z, with respect to Z, we have to take. So sine kz, cos kz. So let me solve it. V prime will be equal to minus mb divided by eik. I have already substituted the a and b coefficients here. Cos kz divided by sine kz. Sorry, cos kz divided by sine kl minus 1 by kl. Okay. Likewise, minus ma divided by ei times k cos kz divided by tan kl this time plus sine kz minus 1 by kl. Okay. So this is my V prime value everywhere. I can calculate V prime. I can calculate V prime at Z is equal to 0, right? And I can calculate V prime at Z is equal to L. Okay. So if I do that, what do I get? I get minus MB divided by EIK 1 by sine KL minus 1 by KL minus MA EIK 1 by tan KL minus 1 by KL. Similarly, and that is nothing but, what do we call it? Theta A. So I've got the value of theta A as a function of MA and MB. You agree? Here, if you notice, for this kind of a problem, the problem that you see here in this diagram, if let's say the P and M were not interacting, this secondary moment effect was to be ignored, what would have been the relationship between, like what would have been the theta value for a given MA MB value? This MA was acting, this MB was acting, what would have been theta A? theta A would have been, if it was as per the earlier discussions on linear systems, would have been MA L divided by,
EA.
are you sure EI or 4EI?
Well,
Isn't it? If MA is applied, it produces a rotation of, or in other words, MA is equal to 4EI by L theta, isn't it? Plus MB L divided by 2EI. Correct? What we are getting here is this value and this value instead of, and there is K also. So instead of 4 and L, I'm getting like L by 4, I'm getting somewhat like this value instead of 2 by EI. Sorry, instead of 2 by L, or 2 L by 2, sorry. So this should have been L by 2. Instead of L by 2, I'm getting this, and instead of L by 4, I'm getting this. Right? So you can actually check what happens if P is equal to 0. If P is equal to 0, what is your K? K is also
0, sir.
0, right? So if K is 0, sin KL is 0, KL is 0. So what is happening? Infinity minus infinity, which you cannot solve, right? So kind of it is a, in other words, it is undefined here. But if you take a limit for K is equal to 0, so K is equal to 0, you cannot substitute directly, because then you are not able to get the solution. It is infinity minus infinity. But if you take the limit for K approaching 0, then you can see that it will turn out to be, it will be very close to the values that we just discussed. Okay, 2 by L and 4 by L and so on. Anyway, moving forward, similarly, we can substitute the value of Z as equal to L, and what you will see is that the terms will only switch, and that is obvious. So what will happen here is theta A, I think this will become, once again, will become minus MA, if I'm not wrong. I don't have it written with me, so 1 by sine KL minus 1 by KL minus MB divided by EIK 1 by 10 KL minus 1 by KL. Okay, and that is nothing but theta B. Okay. Now, these are the expressions for theta A and theta B in terms of MA and MB. The stiffness matrix, what does it do? Stiffness matrix, if you look at the stiffness matrix, where does it fit into the equation? It has force, or that is your M matrix here, MA and MB, you can say. So I will not write it. Force is equal to some kind of a stiffness multiplied by theta A, theta B. Isn't it? So I have to now solve these equations for MA and MB so that I get them in terms of theta and theta B, so that I can get the stiffness matrix. Right now, these coefficients are basically flexibility terms. You agree?
Excuse me, sir.
Yeah.
Sir, you have noted V prime equal to minus MB by EIK cos KZ, right, sir? So there should be KL also, no? Cos KL by sin KL.
1 second. Cos KL by, this is that term, 10 KL. So that is sin KL by cos KL. Is that what you're saying? See,
Sir, in
this
V
part,
dash Z equal to L.
No, sir.
V prime Z is equal to L, you are saying.
Sir.
So first, see, this is the MB term that is going here. Z is equal to L. Okay, let me check. So Z is equal to,
Yeah.
you got it? Is it okay?
Yes.
Maybe
Yes, sir.
I made
Yes,
it.
okay.
Okay.
There is a, but there's sin.
Yeah, you are right. I think I made a mistake here. Let me rewrite it. Let me recheck it. So that is MA term, ME divided by KL, and this will be, why Why did I say this? MA EI by K cos KL divided by tan KL. So that will be, it will be cos, this term will be cos KL divided by tan KL. So that will be sin KL at the bottom. And then plus sin KL term will be there, right? Is that what you're saying? Minus 1 by KL. Is that what you were saying?
Yes, sir.
Minus MB by KL.
It will be
And
1
this
by sin
cos
KL only.
KL divided by sin KL. So that will be 10 KL minus 1 by KL. Yeah. Sorry, I'd missed this one. Is that correct now? And here also, here I think if that is equal to 0, this seems okay. Sorry, am I making a mistake still?
So
See, this is the MA term. That MA term comes here. Cos KL divided by tan KL, right?
Sir, it will be cos square KL by sin KL. Sir.
Oh, I see. Yeah, sorry.
cos square KL by tan cos square KL by sin KL plus sin KL, sir. So it will be 1 by sin KL then.
Okay, cos square KL is 1 minus sin square. Is 1 minus sin square. Minus sin square divided by sin plus sin. Okay, so sin minus sin square plus sin square. Yeah, so 1 divided by sin. But then it's okay. Is that correct?
Yes, sir.
Okay. So I was right in the beginning. I had just kind of skipped.
Yeah. Yes, sir. Sorry.
I had I had skipped a couple of steps in between. I didn't want to write the whole thing. That's why I got confused also. Thank you for pointing out anyway. So, got it? So basically now we have got, this equation is for theta in terms of MA and MB, but we want to develop equation for MA and MB in terms of theta, because we want to develop the stiffness matrix, because we are effectively going to use it in the stiffness matrix method, right? So I solve for it, and basically after solving it, what I get is MA is equal to EI by L KL sin KL minus K square L square cos KL divided by 2 minus 2 cos KL minus KL sin KL theta A plus EI divided by L K square L square minus KL sin KL divided by 2 minus 2 cos KL minus KL sin KL. I hope I am not making a mistake here in copying it from my lecture notes, but it's all available in the slides also. So you can verify it from there. And it's not that complex to solve yourself and try it once. And likewise, MB can be calculated. A square L square minus KL sin KL divided by 2 minus 2 cos KL minus KL sin KL theta A plus EI divided by L KL sin KL minus K square L square cos KL divided by 2 minus 2 cos KL minus KL sin KL. Theta B. Okay, so now these are the stiffness terms. MA is equal to this much times theta A plus this much times theta B. Similarly, MB is equal to a term here multiplied by theta A and another term here multiplied by theta B. These are your stiffness terms for MA and MB. Okay, we can write this as MA, MB You must remember still what are the boundary conditions we had assumed, which is not really a plane frame situation, right? Because we had assumed that the ends are not moving at all. Okay, we got SII, SIJ, SJI, SJJ. What are these? This is your SII because that is connecting MA with theta A. This is your SIJ. This is your SJI and this is your SJJ. Okay. So MA is equal to SII theta A plus SIJ theta B. And if you see, your SIJ and SJI values are same. But in fact, SII and SJJ values are also same. SII is same as SJJ. So not only that, this is a symmetric matrix, even SII is equal to SJJ, which makes sense. So if I introduce a unit rotation here, I get some moment demand here. If I introduce a unit rotation here, I get some demand here. That is basically same as stiffness matrix. Not only that, that is just the symmetric stiffness matrix. Not only that, also if I introduce a unit rotation here, I have to apply certain moment. If I introduce unit moment here, I have unit rotation here, I have to apply certain moment, and this moment is same as this moment. Okay? That is SII being equal to SJJ. That is also obvious for the plane frame member. In addition to that, I can introduce another degree of freedom of axial P, which will be nothing but, I can call it, or what I'll do is I'll take EI by L outside and I'll only call this term as SIJ. I have taken this EI by L out, and these are the remaining part is SII. Okay, so EI by L is taken out. So here what I'll be left with A by I 0 0 0 0, and this is E. E is the axial elongation. Fine. So this is the member that we are dealing with. This was the original position. We applied P and we applied a moment, MA and MB. And as a result, this member deformed. Okay, not only deformed in the lateral direction, it also contracted by an action in the axial direction by E. Okay, so that E is basically still a function of only P. Okay, so E is not affected by the presence of MA and MB, which is again not a fully coupled action. It's I'm assuming it's partial coupling, but MA and MB are affected by, or the rotations theta A and theta B are affected by not only MA and MB but also the presence of P. So that K term basically corresponds to P. Got it? So because of that, I will have some theta A, theta B. Okay, and that's all the things here. Here SII, ideally this term should have been only 4. So in linear case, it should have been SII should have been 4, SIJ should have been 2, SIJ 2, 4 EI by L. That's what it was, right? If you are not convinced, we can go there in the original lecture notes on the plane frame members and show. So for this plane frame member, this is a plane beam actually. Yeah, even for a plane beam, 1 and 3 are restrained now. So the first column and third column you can ignore. So you ignore the first column and the third column, and first row and third row. So basically what you're left with 4 EI by L, 2 EI by L, 2 EI by L, 4 EI by L. So 4, 2, 2, 4. That's what you had. But instead of that, now what we are having is these terms. Instead of 4, we have this SIJ, SII, SIJ, SJI, SJJ. Okay. So this is the new stiffness matrix. The exercise for you, the exercise is calculate the limiting values of SII, SIJ for k is equal to, not k is equal to, k approaching 0. Okay, so this derivation won't work when the k is exactly equal to 0. It will be undefined. But when k approaches 0, what will be the value of k SII This is just a take-home exercise for you. It would not take too long. You can use L'Hospital rule. Are you familiar with the L'Hospital rule?
Yes, sir.
Yes, sir.
Yeah. So if you are familiar with that, please imply that, or otherwise you can check with numerical method also. So numerically, you can make an Excel sheet with these values of SII, SJ. It will just take you 5 minutes, not more than 5. If it's taking you more than 5 minutes, you are doing something wrong. So just make an Excel sheet, keep reducing the value of K in this Sij. So make an Excel sheet for K versus, it will have different values of K and SII and Sij. Write these values in Excel. And keep reducing the value of K and see what happens to these values, or KL you can say. So keep reducing the value of KL and see what happens to the SII, Sij value, which value do they convert to. Okay. All right. So I'll stop here today. Even though we have developed the equations for SII, Sij, still the equations are a little bit more cumbersome. This is useful. This is okay. This is the full derivation. Still, you may remember that for a plane frame, we had developed this stiffness matrix, which was developed for F1, F2. In fact, not only this, for the plane frame, we had developed a stiffness matrix, which had total 6 degrees of freedom, right? So a plane frame had total 6 degrees of freedom. 1, 2, 3, 1, 2, 6, 7, 8, 10, 7, 8, 12. So these 6 degrees of freedom were available. Right now, we are dealing with only 2 degrees of freedom. So at each end, how much rotation is there? All other degrees of freedom have been restrained, or in fact 3 degrees of freedom you can say. At each end, what is the rotation plus axial rotation, axial deformation. So these degrees of freedom are not really degrees of freedom. These are deformations, right? So rotation and axial deformation. We will translate that into the degrees of freedom in the next class, and then we will see the approximate geometric stiffness matrix that was shown in the last slide. In the beginning of the class, I had shown you one slide where we had split the stiffness matrix into 2 parts, the linear part and geometric nonlinear part. So how that is done, we will discuss that. It will be a small class, hopefully, next time. Yeah. So I can stop here today. Anybody has any questions, please ask. All right, then. We'll see you in the next class, Thursday. That will be hopefully the last class.